Hello and welcome back. Today in this video we're going to be looking at torque, introducing torque, and then we're going to connect it back with center of gravity, center of mass a little bit later on. So what we've dealt with mostly so far have been forces, and forces cause a linear acceleration or acceleration in an X, Y, or Z direction or a combination of those. A torque causes rotation. A torque is a force that's applied in such a way that it causes torque, which causes rotation or angular acceleration. So anytime you rotate something, you are applying torque. You are creating torque. When you rotate a doorknob, when you rotate your hose faucet handle, a steering wheel is all about torque. That's why you got a good sized wheel instead of a tiny little wheel. Because you get more torque from a bigger wheel. So just as an example of torque, what we're doing is we're looking down from the above a door. So you're hovering above a door looking down. So this is a wall, this is the hinge, and this is the doorknob, and this is the door itself. So you're hovering from like a sky view. Where is the axis of rotation of a door? Okay, as it pivots back and forth. Well, the axis of rotation is at the hinge itself. So that is the axis of rotation. Now let's say you wanted to open the door. Do you push at it near the hinge? Do you push at it in the middle of the door? Or do you push at it near the doorknobs? Which would make it the easiest. You're gonna get a lot more opening efficiency by pressing at the end of the door by the doorknob. So this has to do with what's called lever arm, and the lever arm is the perpendicular distance from your force to the axis of rotation. So so here we've got this blue would be our lever arm, and see how it's perpendicular to the force. And so if you were to push at the hinge, you would have no lever arm. You would have no distance between the axis of rotation and the force. So you would get zero torque. You would get zero turning power. At B, you get some lever arm, but you get the most lever arm at C. Well, because you're the furthest away. Any force that actually pushes through the hinge, that points to the hinge or the axis of rotation, will produce no torque whatsoever. And will thusly not rotate the door. So if we're applying this equal forces at different locations on our door, or different directions, which one of these is going to be more effective at opening the door? So it's going to be A, because A is perpendicular to the lever arm. B is parallel to the lever arm and points to the axis of rotation, points to the hinge, and any force that points through the axis of rotation creates no torque, will cause no rotation. So the equation for torque, this is not a T, this is a Greek lowercase t called a tau, and that's the symbol we use for torque to differentiate it from time. Torque equals R, which R is our radial distance, which is our lever arm distance, and notice that there's a perpendicular symbol there. So this is our perpendicular distance, okay, from the force. So torque is equal to force times distance, force times lever arm. So the force and lever arm have to be perpendicular in order to create torque. So so let's say you're trying to get a bolt that's similar to our door. Which one of these is gonna? So this is a wrench and this is a hex head bolt, and you're trying to get this bolt loosened up. Which one of these is gonna be better for loosening up that bolt? Well, it's going to be holding your hand at the further end of the wrench, because you're going to get more lever arm. You're going to get more leverage. So because you've got a greater R, you've got a greater lever arm. So if you've got a wrench and you cannot get a bolt loosened, you know what you look for? You look for a longer wrench. Okay, and if you can get an even longer wrench, you'll get more lever arm. And can make a huge difference. Sometimes if you can't get it, you stick a pipe over the end of a wrench and torque on that pipe, and try and get it budge loose that way. So, and of course the more force you apply for a given radial distance, a given lever arm, you're going to get more torque if you push harder. And the angle. Okay, so the more perpendicular you apply your force, to that lever arm, the more torque you're going to get. So if we do apply your force at an angle, okay, then we're going to say only the blue part counts, because the blue part, if we were to break this diagonal into its components of a parallel component and a perpendicular component, only the perpendicular component is going to count. So you could use sine, cosine, tangent to do that. Again, I mentioned this a couple times. Any force that points through the axis of rotation will create no torque. So this force will not cause any torque. Or if I were to come at it from this angle or any other angle you could think of, that's not going to create any torque. So a simple problem, torque on your lug nuts is 200 Newton meters. If you have a wrench, which is 1/4 of a meter, how hard do you have to push? So torque equals force times lever arm. And we're looking for 200 Newton meters of torque. We're looking for the force, and we've got a radial. We've got a lever arm distance of 0.25. Okay, how much force do you have to apply? Well, you're gonna have to apply 800 newtons of force in order to get that torque setting that you want. Real basic problem. I didn't actually work this problem, but I'll tell you how we would work it. Let's say we've got a quarter meter wrench. We're going to apply 70 newtons at an angle of 35 degrees, and we're going to apply 70 newtons. So, if we were to figure out the amount of torque that we're going to generate, what we would need to do is break this apart into its two components. Okay, and we would need to find this component, the perpendicular component. So it would be the sine of 35 equals our y component over 70. We would solve for that component and then multiply that by our lever arm. So we would only use part of the force, okay, but we would use this whole lever arm. As opposed to another method where we can use the whole force and part of the lever arm, and it works out the exact same way. But normally I work out these problems. I didn't see this one when I was working them. So if we look at these two wrenches here, I've come up with a design that I think is going to revolutionize the auto industry. You know how it's cramped inside the engine compartment. Well, I figured out how to make the wrench longer without actually making the wrench longer. And so I think this is going to create more torque for the same amount of length. And is that going to work? Okay, no, because our lever arm is still going to be this distance here. So this bend doesn't do anything except use up some steel and kind of get in the way of some other components probably. So this is still my lever arm distance. So the other way we can look at this is, well, what we've done so far is we've used the whole lever arm distance, the distance from the axis of rotation to where the force is applied, and we only use part of the force. The other way we can do, and there are times when this is useful, there are times when this makes problems much easier. We can use the whole force, okay, but only part of the lever arm. Okay, and you're only doing this when the force and lever arm are not perpendicular. If they're perpendicular, these end up being exactly the same. So anyway, I'm going to show you how to do that. It's not hard. So what you do is, to do the second way, what you do is you draw a line through the force, okay, and then you look for the perpendicular distance from that line to the axis of rotation. Okay, so here's my line that's perpendicular to my force line, and I just move it down until it's perpendicular. And the distance along that line from the axis of rotation to my force line is the lever arm, the shortened lever arm. Now these were perpendicular, so it didn't make a difference. It's just the same as before, pretty much, except for I guess this little nub right here. But we've been kind of overlooking that anyway. Okay, let's look at another couple of examples where it makes more of a difference. So draw your line through the force. So just, and you can do this with a ruler or you can do it in your mind. Okay, kind of sketch it out because we're going to use sine, cosine, and tangent for this. We're not going to get out our rulers and measure anything on this. Now then we bring a line perpendicular to that line until it goes through the axis of rotation. So it's got to be perpendicular to this force line, and it's got to go through the axis of rotation, the center of the bolt. Okay, and now this blue line, the distance from the axis of rotation to the force line, okay, that's my shortened lever arm. See how that isn't going to be quite as long as this? It'll be shortened a little bit. So now we would use all the newtons of force, okay, and whatever this small shortened lever arm distance would be. Okay, I'll work one more example. So step 1, draw a line through the force. Okay. Step 2, look for a line that's perpendicular to this that goes through the axis of rotation. So it should be something about like that. Okay. And so this is now my new lever arm. If I use the entire force, however many newtons that is, okay, I'm going to use this shortened lever arm. So when you work out sine, cosine, tangent on this, it ends up being the exact same thing, your answer. Okay, and this is something that we saw sophomore year in POE, if you took POE, Project Lead the Way. And they really don't explain a whole lot in certain things. They really just kind of expect that you know stuff or just figure it out on the fly. But looking at this, what is the lever arm that we would use for this force right here, this 20 pounds of force? What lever arm would I use? Okay. Well, it's going to be this 9 inches. Okay. If you draw a line through the force, and then look at the perpendicular distance, it's this distance right here, which is that 9 inches. So that's going to create 180 pound inches of torque. Okay. What would I use as the lever arm for this 20 pound force? Okay. What would I use as my lever arm? Well, draw a line through the force, and then draw a perpendicular line to that, and that's going to be this 18 inches. Okay. I don't know how they expect you necessarily to know that without ever having it really explained, but they do that on certain things. So this would be 18 times 20, 360 inch-pounds of torque. Okay. What about this problem here? Let's say I've got a force 100 newtons, and again, I'm trying to get some extra torque out of this. So what I'm going to do is I'm going to apply a rope that's 0.2 meters long to my wrench, which is 0.25 meters long. And I'm thinking this 0.2 meters of rope is going to give me some extra torque because it's getting me further away from the axis of rotation. Okay, so I'm thinking that that's going to help. Well, okay, if I do that second method where we look for the torque, okay, that line, this rope becomes the line that I'm talking about, and again I would look for a perpendicular line to that. Okay, and that perpendicular line is going to be the length of the wrench. So it's not going to give me any more torque. So my torque is going to be force times lever arm, so 25 Newton meters of torque. Okay. Here we've got, I just wanted to approach this with a little bit of math. So we want to figure out the torque that we get by this 70 newtons, which is applied 35 degrees from the wrench, and the wrench is 1/4 of a meter long. How much torque do we get? So what we're going to do is we're going to use that second method where we're going to draw a line through the force. Okay. Then we're going to draw a line perpendicular to that, to the axis of rotation. Okay. So I've got a right angle right here. Okay. And we want to figure out the torque. So what we need to do is look at this side right here. Okay. Well, that's opposite, so that's going to be sine. So that's going to be sine of 35 times 0.25. Sine of 35 times 0.25 equals L. Okay. And then multiply the force, which was 70 newtons, times the 0.143. and we get 10 Newton meters. And this would have been the exact same way, or same answer we would have gotten, sine of theta r times F, if I had broken up this and looked for this component of the force. This force, I would have found this component of the force by the sine of theta. It would have been opposite this line right here. So it works out the same. It's just a way of looking at it that makes it a little bit easier in some situations. Okay, so when we talk about torque, we're generally going to talk about the direction as clockwise and counterclockwise. But this is something that you'll see in college, and you might as well just kind of be exposed to it. It's called the right-hand rule. You'll see it in several different ways in college, in physics, more than likely. And so it's a way of giving the direction of a three-dimensional force or torque, that kind of thing. So what you do is you curl your fingers in the direction of rotation, okay, and your thumb points in the direction of the torque vector, okay. So this is kind of hard to explain without me being there, but so basically, put your thumb in the center of the bolt. Okay, curl it with your right hand. This is called the right hand rule for a reason. Okay, I'm looking at the camera like I'm talking to you guys. Curl your fingers down in the clockwise direction, okay, and your thumb points into the page. So that some of you are going, oh, okay, I get it, and others of you are going, I have no idea what's going on here. So your thumb points into the page, and your fingers curl in the clockwise direction. So that into the page, your thumb points in the direction of the torque vector into the page. So what would the direction of this torque vector point? So this weight is trying to cause this wheel to spin in the counterclockwise direction. Okay, so curl your fingers in the direction that in the counterclockwise direction. Okay, and where does your thumb point? Okay, your thumb points out of the screen, that's what I meant, out of the screen, out of the page. So that would be the direction of a counterclockwise torque vector. Okay, like that. Okay. So the other way we can talk about other than clockwise and counterclockwise is positive and negative. So we're not really going to do that much here either. You might see it this way in college. So for example, this torque right here is trying to cause, if this is my pivot point, is trying to cause a clockwise torque. Okay, so and think about the direction of the force in the lever arm. So my lever arm is to the right of the axis of rotation. It's to the right, so that would be positive because it's in the plus x direction. My force is down, which would be negative. So this would be a positive times a negative. It would be a negative torque. Okay, so clockwise is a negative torque. And over here on this side, I've got a negative lever arm. Okay, my lever arm is in the negative x direction from the pivot point. And I've got a negative force. Okay, so that's going to give me a positive torque, which would be in the counterclockwise direction. So it would be trying to push this down and causing it to pivot up like that. So we're not really going to deal with it like that. We're just going to stick with clockwise and counterclockwise. You can always make the transition in college. It's not that hard. So what we want to do is figure out the net torque acting on the seesaw. So let's look at this side right here. We'll look at this side, make that. So this side, okay, is going to cause this end to pivot down, which if it's pivoting over this is going to be counterclockwise. So my lever arm is 4, it just gives me, and the force is 20. So I've got 80 Newton meters of counterclockwise torque. Okay, over here, we've got a lever arm of 2 and 30 newtons, so we've got 60 Newton meters of clockwise torque. Okay, so these are just like ups and downs. They cancel out partially because they're in opposite directions. So what's left over is going to be 20 Newton meters in the counterclockwise direction. So that would be the net torque. Okay. What would the net torque on this wheel and axle system be? So if this is a large wheel and then this is a smaller diameter wheel connected to it, and we're pulling down on these two things, what's the net torque going to be? Well, this 80 Newton force right here, which way is that going to cause it to rotate? Clockwise or counterclockwise? Okay, this is going to cause a clockwise rotation. Okay. This guy over here is going to be a counterclockwise rotation. So let's calculate each. So we've got, so for the 40, we've got 0.1 lever arm. So the radius of a system like this is your lever arm if you're dealing with a wheel type of thing, or an axle. So 40 times 0.1 gives me 4 Newton meters counterclockwise. Then I've got 80 times 0.25 gives me 20 Newton meters of clockwise torque. So I subtract them because they're in opposite directions, and I get that I've got 16 Newton meters of clockwise torque left over. Now, if there's a frictional torque like down here, that's always going to act opposite whichever way that it's rotating. So if it's rotating in the clockwise direction, then the frictional torque is going to act opposite that, and we would subtract that off to get 13 Newton meters of clockwise torque left over. Okay, skipping that. So what I want you to do is go ahead and have a stab at the first torque worksheet that goes along with this stuff. And if you have any questions, see me on office hours.